here we go on day 2 of special relativity. We have, what is it, 1, 2, 3, 4 major things to hit today. I'm going to begin with this triangle, or this idea that we ended with the other day, and it is the fact that light's going to go up some distance L and come back down, okay? And we talked at the end, how much time should that take? What's that? No, that's a velocity. We'll just use that constant velocity equation. So what distance is it going to go? L. It's coming going up and back. 2L. 2L. So remember, I mean, I'm just using this. Displacement is velocity times time. So time is just displacement divided by velocity, right? So displacement is 2L. It has to travel 2L. And what velocity is light going? C. Light always goes C, correct. So that is how much time it should take. How much time it should take for, so if I'm sitting here with a flashlight, I turn it on, goes up, it hits the thing, comes back down, that's how much time it should take. Meaning, really basic stuff like, somebody asked me again today, they said about, they were a little bit confused about the looking further into the past thing, so I did some really basic math for them. I said, okay, so that chair sitting away from me is 2 meters away. So I take 2, the distance is just 2 meters, divided by the speed of light, 3e to the 8th. That means I see that chair 6.7 nanoseconds ago. Now, is my brain going to be able to register 6.7 nanoseconds? No. My human reaction time is like 150 milliseconds, which is like, a billion times this number. I'm not going to notice that. Even if I look at the back of the room. Okay, well, if I look at the back of the room, it's 12 meters away. And I take 12 divided by 3e to the 8th. And it is 40. It's 40 nanoseconds away. Okay, now obviously I'm not going to be able to notice those distances, but is the back of the room further away in time than the front of the room? Yeah, so not only is it further away in distance, but it's actually further away in time, aka the back of the room is further in the past.
I just said that that's the past, though, and that's is that.
Well, they both are. They both are. Like if I could okay, so let's say for example I could look left and right here, and I'm looking at the same distances. They are equally as far in the past. It's not a matter of this way is past and this way is future. No. Okay? I can't look, here's the weird thing. I can't look at now. I can't. If I look at my hand, am I looking at my hand now? Okay, now am I looking at it sooner? Yeah. Sure. Good. Am I looking at my hand now? No, I can't see anything anymore. There's no light because there's no distance. There's nothing to hit in there. So it gets really messy as far as I cannot actually see now. All right. Do we kind of understand this time that I've made here? Okay. It's how much distance over how much velocity is going. Cool beans? All right. So now we put this person on a train that is traveling a speed of v. Does the person see the same thing they saw a minute ago? Yes. The person on the train still sees the same thing. Why? Because they are at rest to the event. When I say they're moving at velocity v, who would see them moving at v?
The observer.
Yeah, somebody over here on the side, right? This person watching them, okay, sees them traveling at v. How fast do they see themselves going? 0. They're just going. It's like saying you're standing on the ground. How fast do you see yourself going? 0. You get in a car going 70 miles an hour. Who sees the car going 70 miles an hour? Somebody outside the car. How fast do you see the car going? No. 0. Right? And the reason why is because you're going the exact same velocity as the car, right? So this person up here, okay, is going the exact same velocity as the car. So I'm going to give a name. I'm going to give a name to this time. I'm going to call this time proper. Now, time proper makes you believe that is sort of the correct one. That is the terminology that's used in physics. It is not necessarily the correct one. It's just the definition. Time proper is defined as the time that the person at rest to the event sees. So let me break that down. What's the event? The light going up and coming down. who is at rest to that event? Person on the train. Does that make sense? Okay. So let's remind ourselves what this person sees. Well, this person would see this. What we're going to try to do now, a little bit mathematically, is we're going to look at that triangle. We'll just use some basic geometry to figure out how does those lengths, how does that, obviously it's going further, right? And we shared yesterday, sadly, velocity can't get faster. So if it goes further and velocity has to stay exactly the same, what must be the case so that you can see it go further? Meaning this person should see the same event take longer than that person right there. Does that make sense-ish? Okay, so what we're going to do is we're going to look at the triangle and try to figure out how much longer the triangle is than this right here, so that we can then figure out how much more time they're going to have to experience. Does that make sense? Okay, so I'm going to look at one portion of the triangle right here. Okay, and I'm just going to use distances. Which part of the triangle do I know in terms of distance? L. I know L right over here. Okay, and then I'm going to use this equation that I actually nicely have sitting here to measure the distances of the other. How fast is something traveling along this side? C. And how much time should it take? Well, this would be the new time, except it's not all of the time because I'm just going up. How much the time is it? Half. So I'm just going to take that and divide by 2. So this is the distance when you've got the velocity of c at that particular time. Okay? And we're going to do the same thing on this bottom row right down here. This bottom line. How fast is it going along this line? V. And how much time is it going to take? Half of whatever this new t is. Okay, so I got all 3 parts of the triangle. I'm not trying to use trig to figure out one of them, so I'm just going to use trig to put them all together. And the goal is going to be to find this term so I can compare the new time to the old one. Does that make sense? Okay, so how do I compare this? Well, that's going to be, this is just trig, so that's going to be L squared plus what? I'm just going to square it all while we're doing this, yeah. Is equal to? The same thing, c squared times t prime squared. All right. Now my goal, like I said, is to take this mess and somehow pull out 2L over c. What would you do here to simplify first? No, you can't. I mean, you sort of can, but it makes it messier. I think
you're trying to get what?
We're trying to get 2L over c. Let's just say this. Eventually, you want to isolate just the t prime, because that's the new time. Okay? But even easier than that, first thing I notice is fractions. I got 2 fractions. I'd rather have no fractions, so what should I do? Multiply everything by 4. And there we go. The next thing I'm doing, since I'm trying to get like t by itself, is I'm just going to get the t's all on one side. Make sense? So I have 4L squared is equal to c squared times t prime squared minus v squared times t prime squared. And I'm going to math magic this with the board and factor out t prime squared. What's next?
Divide by the c squared minus
Yeah, divide by that whole mess. Absolutely. 4L squared, c squared minus v squared. And then what should I do last? Now we square root everything. Okay. Since this is a division thing, I can square root the top and bottom separately, right? What would the top part be after square rooting?
2L.
Hey, that works out nice. 2L. Okay. Over what? The square root. No. That's not how that simplifies. Over the square root of c squared minus v squared. Now I told you at the beginning of this that I wanted to pull out a 2L over c. And you might remember from the math yesterday, we know exactly how to do that. What should we do up here to pull a c out of the bottom term?
Take the c out and then put.
Not quite the c out. Take factor c squared out of both of these, just like we did yesterday.
And then you get 1 minus v squared over c squared.
You get what?
1 minus v squared over c squared. No.
Where did the c squared go? Hold on a second.
Like outside.
Let's do it like this first. You're right-ish. That's essentially what it is. Okay. Now what can I do with this? Since they're multiplied, yep, we can square root it. So now I've got this. Okay. So the new time is equal to this mess, where this right here, this right here, is time proper. Yes? So I'm going to say that time dilation is equal to time proper times 1 over the square root of 1 minus v squared over c squared. And to make our lives easy moving forward, because that's a lot of writing, we're going to give that its own name. We're going to say that gamma, which I think is the time dilation factor, is equal to 1 over the square root of 1 minus v squared over c squared. So essentially, I'm just turning this guy into this constant. And now I can write time dilation as this. Time dilation is equal to time proper times gamma. Now, gamma is both complicated and actually arguably very easy when looked at from the right perspective. Okay? It's hard because you look at this whole mess and you go, oh, that's icky to possibly use. Okay? But actually it's really easy to understand when you don't focus on this and focus on this equation instead. What is gamma? Well, gamma is, if I just move this underneath, the ratio of how much time one observer gets compared to the other. So to put in perspective, we've actually sort of already used this ratio when I did my example yesterday, and I said I wanted to be the same age as you. I said for 1 year of my time would be 24 years of your time, which means gamma's 24. Now, does time have to be in years? No, I said that when I said seconds. For every 1 second of mine, you would receive 24 seconds. Gamma is 24. Gamma is the ratio of time proper to time dilation. Let's put this back over here.
And which one was time proper?
That's what I was going to get into next. Okay, to understand that, you got to go back to this definition that we started with right up here. Who's getting time proper?
The guy on
the definition I said was the person at rest to the event. So what is the event here? No. The light itself going up and going down is the event. Who's at rest to that event?
At rest, like they're viewing the event at rest, or at rest, like the event's happening.
So this goes all the way back to relativity, and students struggle, as I told you back in relativity, with the whole like, okay, but like rest is the earth, right? Like rest is, nope, you are not at rest right now. You are not at zero. You are traveling very, very quickly. If you want to compare yourself to the center of the earth, you're going really fast. If you want to ignore that, you're spinning around the earth, which means you're going really fast. If you want to ignore that, our solar system is going around the Milky Way galaxy even faster. We have a velocity. It only appears like we don't, because if we look around, everything else is going the same velocity as us, right? It's the same idea as if I am in a car traveling 80 miles an hour. How fast does everything inside the car appear? So the Earth, this classroom, and everything is the car going 400 meters per second. It just appears like it's not moving because we're all going 400 meters a second. So what does rest mean? Rest means same velocity. Rest means 0. So who's going to see time proper in this? Right here. There's time proper. That's the person at rest to the event. This is the weird part. So who's moving compared to the event?
The guy that's standing still.
And keep in mind, they are moving that way to the event. Does that make sense?
Negative velocity.
Sure, if whatever the other way. Is all I'm saying. So in my example that I gave you, I said that I want to go out on a rocket ship. What is the event in that particular case?
The rocket ship.
Me leaving on the rocket ship and coming back. Who's at rest to that event?
You.
So I get time proper.
And
you're moving relative to the event,
would be like
so you get time dilation.
where are you moving though? Like you're going up, we can't go down. Why we could like up here to go down, but we're not really going down.
So this again, it goes back to relativity. Let's play this game. I'm gonna walk this way. Who's moving? Me or you?
You. But like to me, you're moving. We're both moving.
Yes.
You push through that way.
How do I know that I'm moving this way? If you were in a car, what do you look at to let you know you're going 60, 70 miles
My
an hour?
speedometer.
No. I mean, sure, you're not entirely wrong, but let's say
See the trees moving past.
you're looking at everything else going the opposite way. You're watching them move.
And it's my
the opposite.
intelligence to know that I'm the one that's moving.
Intelligence or predisposition, however you want to put it. Yeah. Okay. Do this for me then real quick. Let's come over here. We're going to practice with this guy just one time. If we were getting really into this, I'd probably have you do it 2 or 3 times just to get used to it a little bit more. First thing I want you to say is, what if my velocity was 80% the speed of light? This is how you usually write this. You don't usually write it as like, the actual number, which I think would end up being, 90% speed of light is 200. It'd be 240 times 240 million meters per second. I think is the exact number here. But this is usually how you write it. Okay. Why do you usually write it like this? Well, because watch what happens when you plug it into the equation. I go 1 over the square root of 1 minus, instead of v, I'm going to write 0.8c squared over c squared. What nice thing is about to happen? The c squareds are going to cancel. Now, what's this top part going to become? 0.64 c squared. Right? And then we cancel c squareds and go ahead and finish that off. Go ahead and finish it up. Calculator or whatever. What is the gamma factor for something going 80% the speed of light?
And is there no units now?
What's that?
No units.
Oh, wait. What would the units of time dilation be?
Well, I would think seconds, but there's no seconds.
So look, it's going to be a ratio again. See, this is not seconds, it's t
So
over
it's like
t.
mu.
It's like mu, it's like one
Every other
force factor. Yeah, a lot of them, not all of them. What's that?
1.67.
1.67. So that's insane when you think about it. 80% the speed of light is very fast, and that's only changing your factor by 1.67. So if I tried to pull off the trick I told you yesterday and I was going 80% the speed of light, I would go out for a year and come back, and you would not even be 2 years older.
But isn't the time dilation, the closer you get to the speed of light, isn't it like exponential?
It gets very quick, yes. Yeah, you're right there. My point is just this. Usually we do not consider relativistic effects. We ignore relativistic effects until it gets bigger than 1/10 of the speed of light. Okay, now 1/10 of the speed of light sounds kind of small, but keep in mind, if the speed of light is 3 times 10 to the 8, or 300 million, sorry, all right, no, yes, 300 million meters per second, 1/10 of that is 30 million meters per second. It's got to be quite up there. Okay?
How fast does a rocket usually go?
Nowhere close to that. Absolutely nowhere close to that. I don't have a number off the top of my head that I could give you. I'm kind of interested now myself. But let's play this game. Let's switch it up. What if I said instead, how fast do you have to go to get a gamma of 2?
We gotta find.
Do the math. You're going to want to write this algebra down, pretty sure. This is where you're starting. I'll do the math
And
with
we
you, but
have
I'll
the
let you
same
plug it in.
velocity.
All right. How do you want me to start here?
You gotta solve for b squared or for b.
All right. So what do you want me to do first?
Multiply the whole thing by that rough bottom square root. Or you can take the b squared out.
I see what you're saying, but I think there's an easier way to do it. Let's just invert both sides.
Oh, you move the 1r over.
Yeah, algebra.
Then you square both sides.
Square both sides. Okay, I like it. Which is just, that's going to be 1, so I'll put a square on this.
And then I would. It's going to be 1 minus 1 over r squared equals b2 over.
There's no r. That's a v. Sorry. You said what now?
It'll be. I meant like it'll be 1 minus 1 over gamma equals b squared over c squared.
You got it. All right, so I'm going to add this and subtract that is what you're saying. So v squared over c squared is equal to 1 minus 1 over gamma squared.
And then you multiply by c squared.
I'm going to multiply by c squared. And?
Square root.
Now, in this, keep in mind that this whole thing is multiplied by c squared. I'm going to show you this because it makes it a lot nicer. Watch here real quick. I'm going to square root this, but then I'm just going to take this off because that's c. Now, again, you don't really have to worry about c. This right in here is just going to be the fraction that we're looking for. Do you see that? It's going to be velocity equals this fraction of c. So tell me what you get.
R is 2.
Whatever the square root of 0.75 is.
1 minus 1 over 4.
Pardon the interruption, but technology is ready for the last 3. Students with the
0.866.
last name that are
Yep. So you got to go, I think I'm just going to go to the third decimal at 86.6% the speed of light in order to get a gamma of 2. Okay?
So does gamma have like an actual value, or is it like?
What do you mean a value? Because we just said the value is 2. Are you asking units?
Oh,
What does
2.
gamma mean?
Gamma is, go back to this guy right here. Gamma, by definition, is the ratio. Let's say I get on a ship and I go 86% the speed of light and I come back. Gamma says that I will get, let's say I go out for 1 year, it will be 2 years for you. So in my example the other day, where I went out 1 year and you got 24 years, the gamma was 24 to 1. Now, you don't have to go for a year. I keep using a year. It could be minutes, it could be hours, it could be seconds, which is why it's technically unitless. It's just a fraction. If I go out for an hour, 2 hours would happen for you. Does that make sense? And again, I reiterate something. It's not a perception thing. If you had the most accurate clock that never messed up, never slipped, and you put them, they're lined up and they're exactly lined the exact same way, and you put one on the rocket ship and one on Earth, and that rocket ship goes out for an hour and comes back, and they both time it perfectly, the one on the rocket ship will read 1 hour, and the one on Earth will read 2 hours. It is how long it has actually taken for different groups. Yes.
Oh no, I just meant.
Okay. Yes. Fair enough. All right, let's enter into what's known as the twin paradox. The twin paradox essentially tries to explain a lot of the stuff that we were just talking about. Okay, it starts off with, and paradox, of course, means it's broken. Now, time dilation is going to be involved here. Time dilation is not the paradox. It's accurate. It's weird. We've seen it. We've measured it. Time dilation happens. Not usually, because most things aren't traveling 1/10 of the speed of light, but it does, in fact, affect things on Earth. We could talk about that later. So let's say we've got 2 twins. One twin's going to go in the rocket. We'll call him Speedo. The other one's going to stay here on Earth. We'll call him Go Slow. They're Russian. Okay? For the argument of what we just got done saying, I'm going to say that Speedo is going at a velocity of 86.6%. I said that poorly. Hold on. 86.6% the speed of light. Why? Because we just figured out a second ago that that velocity has a gamma of 2. Fair enough? So, now, speedo travels out to a planet that is 10 light years away, and then travels back. So how far did it take? 20 C. And how fast was he going?
0.866.
So, time is just distance over velocity. And actually, you'll notice nicely the C is canceled. So what's 20 divided by 0.866?
Roughly 23.1.
Okay, I like it. 23.1. So if those are in years, this took 21, what is it, 21.1? 23.1. Sorry. Years. The messy bit here is who got the 23.1 years.
Speed
Well, who would have measured the planet?
Well,
Go-Slow would have. Go-Slow would see that the planet is 10 light years away. Or, I'm sorry, let me say that differently. If Speedo and Go-Slow are standing on Earth, then they're exactly the same. So they would see hit it 10 light years away. Okay? And who would see it going at 0.866 C? Well, technically both of them, but Go-Slow would see it. So this right here is Go-Slow's time. That is Go-Slow's time. Okay? Who gets time proper, though?
guy up.
Who? No, careful with that. Who's at rest? What's the event?
They're going on the rock.
The rocket going out and coming back. Who's at rest to the event? Speedo. Speedo is at rest to the thing that's happening. So he gets which time? Proper. So this time is time dilation over here. Okay? Does that make sense? So we do a little bit of math. We go, all right, so time dilation equals time proper times gamma. So time proper must equal time dilation over gamma, or 23.1 years divided by 2. I did not make numbers easy for myself. Help me out. What is that? 10, 11 point, yeah. So Go-Slow. So who gets 11.6 years? Speedo. So they both started off at the age of 30. Speedo is now 41.6 years old. Go-Slow is now 53.1 years old. He is older. It is noticeable. Almost a decade has passed between the two of them. So Go-Slow gets mad. Go-Slow says, this is stupid. I did the math. It's super basic math. I don't understand. Einstein's postulates is light always goes C, but if you remember I said the other one yesterday, everybody should agree on physics if they're going the same velocity. Physics should still work. This is super basic physics. So, Go-Slow does the math for his brother, what we just did. Literally says, this is stupid. It's 20 light years away, going 0.866 C, so you should 100% have taken 23 years. And Speedo looks at him and goes, I agree with you about my speed. I was 100% going 86.6 pursuit of light because I don't know what you're talking about the planets being 10 light years away. The planets are only 5 light years away. See, for Speedo, if the planet was only 5 light years away, how long would the trip have, or how far would the trip have been? 10 C.
How do they just think that?
Hold on, I'll get there. And then if we take his 0.866 C, this is the time of Speedo. So how long should it have taken? 11.6 years, exactly what we got just a second ago. So what that means is not only is time dilation a thing,
Depth dilation.
length contraction is a thing. Changing your velocity doesn't just change the rate that you travel through time, it changes the freaking distances themselves. The size of the universe got 2 times smaller for Speedo because of how fast he was traveling.
How did it get smaller?
Length contraction.
But why length contraction? Like we're just saying that the universe. I get the whole like light relativity like thing. Like I understand that, but how can the universe just like it's smaller now? Like I get it that it happens because you're telling me, but
Then you get it. Look,
I'm not getting it.
there's not getting it versus not getting it. A lot of times comes down to do you not understand or do you understand? And you're just like, ooh, that's icky. I don't like that. I'm not used to this. I'm going to argue it's probably more the second one than it actually is the first. Because the answer to your question essentially is right here. The rules of physics still have to work, right? Let's work this way backwards, okay? If Speedo is going 80.866 C and he only traveled 11.6 years, basic physics says he could have only traveled a total of 10 light years. Physics still has to work. So how does it work? Well, and it's kind of what we said a second ago. I mean, it feels backwards, but look here. Look back at this example we already have. We sort of already have length contraction. Who got the larger length of this event?
The guy on the ground.
So
It was faster
for the person in the train, the length has been contracted.
But wasn't that just because the time was shorter or the time was longer?
They go hand in hand. One without you can't have one without the other.
So light can change the time and distance?
Yep. And it's not the only thing.
Is it because
Hold on.
time
I got 2 or
longer?
3 major things to hit in the next 15 minutes, and I'll tackle any questions that you have. I want to make sure and hit these, especially for anybody watching the video a little bit later on. So here's what we have right now. We have time dilation and length contraction. So time dilation is this. It is time proper times gamma. Now, you would love it if all of the propers matched up. Sadly, they don't because this. Okay? Time proper, by definition, is the time measured by the person at rest to the event. Okay? Length proper is measured by the observer at rest to the length. What is the length in our last example?
The planet.
Not the number, just what is it? Yeah. It's the distance from Earth to whatever planet or moon or whatever they were going to, right? Who would be at rest to that length?
The guy on the
Which guy? Go slow or Speedo? Go slow. So why Speedo got time proper, because he was at rest to the event, Go slow gets length proper, because he's at rest to this length. 20 light years is length proper. And you'll notice that that works on my math, because if I plug in 20 light years and gamma is 2, that means that Speedo should have had length contraction. The entire universe gets smaller. When I mean the entire universe, it's crazy to play out. It means planets would shrink along that direction. They would no longer look spherical. Okay? It means that the atoms themselves would actually have different distances between the atom and the next atom and the next atom. It's insane. Yes?
So are they like, it's just shrinking for the person going at that speed, right? Or
Yeah.
is it actually?
And they're both lengths correct.
Both of those are true. Again, when I said the other day, I said who gets the right time? Who gets the right length? I know it's messy and I apologize. I told you yesterday was just the tip of the iceberg and I'm not done yet. All right, I got 2 more major things to hit. I said at the beginning of this is called a twin paradox. Neither time dilation or length contraction, which I use the twin paradox to introduce length contraction to be fair, but these are not the paradox. These are consequences of the postulates that Einstein starts off with, that all physics has to be the same for inertial reference frames, and light always goes at c. This is what we mean. What you're dealing with in your heart, like, ooh, is what I said yesterday when I set up, well, physicists were all like, well, we can believe all of physics or we can believe C. I like all of physics. That doesn't seem right. It feels icky. It's all that. And a bag of, yeah, whatever. But these are not the paradox. The paradox goes back to relativity. Okay? So here's the planet. Here's Earth. Okay? Here's Speedo. Okay? This is what all of us kind of imagine. Speedo goes out and comes back. Okay? Just like I'll represent Speedo here. Here we go. Okay, I'm gonna walk out, and I'm gonna come back. Except from Speedo's perspective, if he has like windows in the ship, like if he has windows behind him, would Speedo actually see the ship move?
No.
How do we know that the car is moving? We look at everything else. So how would Speedo know the ship is moving? So what would he watch Earth do? Go out and come back. So Go Slow sees this. Speedo sees this. So who the heck is moving? Those motions appear entirely symmetrical to each other, and yet obviously they don't get a symmetrical result, right? One is definitely older, one is definitely younger. So rather than, again, I'll write this up here because I stupidly forgot we were recording. Okay, so again, here's what Go Slow sees. Speedo come out and come back. But here's what Speedo sees. The planet come out and go back. They appear to be symmetrical from opposite perspectives. So why are they not? We're going to touch briefly on general relativity. Imagine, if you would, the moment that Speedo turns around right over here, that he's holding a very full cup of coffee. And Go Slow is over here on Earth and happens to be holding also a very full cup of coffee. The moment Speedo turns around, is there a difference in the cup of coffees? No. Yes, there is. Who's going to get a large difference in the cup of coffee?
Like,
all right, imagine I'm Speedo, okay? You're Go Slow. Imagine you are holding a cup of coffee and I'm holding a cup of coffee, okay? I turn around quickly.
Oh, your coffee spilled.
Why did my coffee spill?
Because you quickly changed your velocity.
Oh, I need a different moment. Nope, need a different word. You're not wrong.
Inertia.
Inertia. I switched inertial reference frames. I accelerated. Who accelerated up there?
Speedo.
Speedo. By accelerating, Speedo becomes the event. That's what decides that time proper. Okay? Gets really deep into general relativity. I don't have time for that. I got 10 minutes to cover the last thing that I really wanted to hit that I think I told you I would do on day one, and I want to. So I want to do that here real quick. But essentially, the paradox solution is that the paradox is, again, this is not the paradox, time dilation or length contraction. The paradox is that their motions appear symmetrical from relativity standpoint, but they do not get a symmetrical result. And the solution is that you're not symmetrical because right here, Speedo accelerates. Therefore, he switches inertial frames of reference. Therefore, he switches the rate at which he travels through time. Therefore, he becomes the event. Therefore, he gets time proper. And over here, Go Slow doesn't switch at all. If he's holding a cup of coffee, it just stays full at that particular point in time. Now, if, this is a crazy thing, if, let's say, Speedo, instead of deciding to come back, decides, you know what, I'm never going to come back. I'm just going to go forever. I'm just going to keep going as long as I possibly can. And in a super weird thing, well, not a super weird thing, okay? So here goes Speedo over here. Let's just move him. Here he is, okay? So Go Slow misses his brother and realizes that he's never coming back. So he decides to get in another rocket ship and accelerate. Now, he has to accelerate even more. Why does he have to accelerate even more? He's got to go faster. He can't go the same speed. Same speed means he'd still never catch it. So he has to accelerate even more and go even faster to catch it. Since go slow accelerates to catch up to him, when he catches up to them, it's flipped. He's time proper, which means go slow is now the younger one, and speedo is now the older one in that case.
Because time shrunk, because the distance shrunk more. He gets faster.
All right. Last piece, and then I'm done for the year. So, time dilation, length contraction, and way too quickly, I'm going to give you this one. Mass expansion. If time proper is the time experienced by a person at rest of the event, and length proper is the length measured by the person at rest to the length, guess what mass proper is?
Person at rest to
the mass. So if we're looking at the rocket ship, you and I, and we're sitting next to it, everybody's going to agree about the mass of the rocket ship, yes? And the rocket ship takes off. Who would be at rest to the rocket ship? People on the rocket ship, right? They'll experience the mass just like normal. What will we experience the mass do then? Go up and up and up and up. Now, let's talk briefly what happens as V gets bigger. What happens as V approaches C? I'm going to use a little bit of pre-calc limits here. What happens as V approaches C, then this whole term gets closer to 1. Not at 1, closer to 1. 1 minus that closer to 1 means this heads towards 0. Now square root's going to slow that because it's going to make it a little bit bigger, but still the whole bottom part is headed towards 0. As the bottom part heads towards 0, the whole thing heads towards infinity. Now, it doesn't happen obviously quickly. We've already seen that to get to 90% the speed of light is only going to affect things by like 2.3 or something like that. So it doesn't happen quick, but it does happen. Now, watch this. Let's talk about this. Why can't we go faster than the speed of light? Well, sitting on the rocket ship, we had this conversation already. We can't get closer. It's easy. We can't get any closer. But you would see yourself go faster and faster and faster, but no matter how fast you turn on a flashlight, what are you going to see light travel at? C, always. So from the perspective of the spaceship, the answer is easy. Why can't we break the speed of light? We can't get closer. End of story. But what about people on Earth? Are people on Earth seeing the rocket ship get closer? Yes. I can explain this, though, with two pretty basic equations that you guys should know pretty well. All right. So, this thing goes faster and faster and faster and faster. What happens to this? It's bigger and bigger and bigger and bigger. So, what happens to our viewing of the mass of the spaceship? The mass of the spaceship gets bigger and bigger and bigger and bigger. So as the mass of the spaceship gets bigger, same amount of force, what starts to happen to the acceleration that we see? Smaller and smaller and smaller. So the rocket ship is still speeding up, but it's speeding up slower and slower and slower. Now there's your answer, but watch this. Let's talk about energy very briefly. You put energy in, you push the gas pedal down, put coal in the engine, whatever rocket ships run on. Okay, you put energy in. From the perspective of the spaceship, you put that energy in, it's just like a car. What's going to happen? You should go faster and faster and faster and faster and faster, right? Just this guy right here. AKA, from their perspective, all that energy goes into speed, right? Except for us. Do we see all that energy going into more and more and more speed? No. Conservation of energy. Where is the energy going if it's not going into speed? So what you just told me is that energy and mass are the same thing? E equals mc squared. Energy and mass are the same thing. Mass is just a very densely stored amount of energy. The amount of energy stored in 1 kilogram is 3e to the 8th squared. 9 times 10 to the 16 joules is stored inside of here.
But you can only like extract it if you accelerate it to the speed of light, right?
More nuclear bombs.
But I feel like that would still be like super inefficient.
We'll talk about it next year where we legit use it all the time.
When
Do
you
you
said
start physics 2 with this, or do
No.
you end it?
About 3/4 of the way through.
Because
When you say we can't get closer, what did you mean again? I know you said that yesterday, but like,
What I mean is, okay, so
can't get closer to what?
the speed of light. So like, let's put it in numbers that make sense. So like, let's say I walk away from you at 4 meters a second, okay? And Chloe's in between us and she walks at 3 meters a second.
Gotcha.
Logically, you would go, how fast does Chloe see me?
1 meter a second.
Correct. So what I'm saying is light is weird like that. If I am behaving like light and I always leave you at 4, and Chloe's walking away from you at 3, you would expect normal relativity would say she sees me at 1. But if I'm acting like light, how fast would she see me going?
Let's see.
4. Right, C. The exact same.
Gotcha.
No matter how fast Chloe goes,
We can never
to
go
you.
fast enough.
And again, it's so weird to say like to you, right? Because how fast does Chloe see Chloe go? 0. Chloe's always 0. So if Chloe is always 0, or I mean all of us are always 0, it kind of makes sense. If we are always at 0, how fast is light always to us? C. Because I can't go faster compared to me. I can only go faster compared to you. You see me moving. I don't see me moving. I can't see me moving. I see the rest of Earth going the other way. So there you go. I told you I would end with E equals mc squared. Hopefully it was. How did we feel? Was it worth it? Was it a letdown? How did you feel?
Magical.
well, maybe it would help if there wasn't such a discrepancy in the comprehension. Because obviously you understand it more. But I mean, like I don't know.
Do you see what I'm trying to get you to come with? Like, if you put the gas in, you would expect to go faster.
Yeah.
Right? And if you're in the rocket ship, like if you were like dropping rocks, like you were dropping rocks like every 10 minutes, you'd see yourself go faster than the rock. You'd see yourself speed up, 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 right? Okay? You always see yourself speeding up. But if that's happening to this rocket ship, as we are watching the rocket ship go at 99% the speed of light, can the rocket ship see itself double in speed? Sure. At 99%, can we see it double in speed?
Yeah.
No, because it can't break C. So if it's at 99% the speed of light, we're going to see it go like 99.5. So did the energy go into speeding it up?
No.
Wait,
So where did all the energy go?
which
Energy
does
goes-
that make the mass bigger?
And yes, more inertia. It's like, it would be like, from our perspective, it would be like, imagine I'm walking around and I just get like 2 Spain hours bigger, 3 Spain hours bigger, 4 Spain hours bigger. What would happen to my ability to accelerate?
It would slow down. And once you slow down,
So it'd be
you-
harder to get faster and faster.
And
That's
then you slow down
exactly
and
what
you
you're
lose
looking
the
at
mass.
right now. Yep.
So basically,
Gravel,
like I know you said obviously everything has to follow the laws of physics. So like to accommodate for it getting closer to the speed of light.
There's a lot of other pieces on the proof of why the contraction works that I am avoiding for this disparity of trying to get through this in 2 days, as opposed to spending the probably more appropriate amount of time to let your brain come to terms with it. So there are certainly other and better ways to explain it, but that is one way to say is that, look, the laws of physics for the same inertial reference frame, meaning if we're going the same velocity, we should still 100% agree on the rules. Yeah, he can't go 86.6% the speed of light for 11.6 years. How much distance can he cover? 10 light years. Pretty basic math there. That's all he's got. Because that's all there was. It doesn't obviously work like that. That's just kind of our, like, why did it only take him 11.6 years? Because he only had to travel 10 light years, not the 20 that his older brother, experienced.
Have a good summer, Spain hour.
You too. Good luck, everybody online.